Chapter 7, Section 5, Solving Systems of Linear Equations by Elimination. Now, the first method that we used was called the graphing method. And I like that. That's fine. It works out okay, especially if I have graph paper and the equations aren't overly complicated. Because when you graph them, you get kind of a picture of what's going on and you can see your solutions maybe a little bit better, whether you have one solution, zero solutions, or infinitely many. Now, I like the substitution method better than I like the graphing because with substitution, you can get exact answers even when there's fractions involved. With graphing, you'd have to have a pretty accurate graph to get an answer that might be like an ordered pair, like 5/8 comma negative 2/3. That'd be tricky to come up with, but not with substitution. There's one problem with substitution in that you have to have one equation in terms of the other. And that doesn't always happen. Sometimes in the process of trying to solve for one of the variables in one of the equations, you might end up with fractions, and then that can get a little bit messy as far as the arithmetic and the algebra is concerned. All right. Now, there is another method. This other method, this book calls the elimination method. The elimination method in some books is sometimes called the addition method or even the linear combination method. I kind of like the linear combination method myself, but that's a lot to say, so most times I'll just call it the addition method. And what we're going to do here is we're going to go over the rules for the elimination method so we can see if this will come in handy. And this mostly is coming in handy when the equations are in standard form. Now we'll talk about that. But the elimination method uses a property of algebra that says if A equals B and C equals D, then A plus C equals B plus D, which is saying if we can add equal amounts to the two sides of an equation and end up with an equal amount. I always think of it as like a teeter-totter. If A is equal to B, if one side of the teeter-totter is equal to the other side of the teeter-totter as far as like the weight, and then we have two people that want to join and they're of equal weight, and we put one on one side and we put the other one on the other side, we should still have that equilibrium. We should still have equality as far as their weights. So we're going to use this idea in the elimination process. And of course, the elimination name means we need to eliminate a variable. Now, we did that with substitution. I'll show you how to do it with using this property next. So we're going to try to eliminate one of the variables so that we end up with an equation that has only one variable in it. Because if it only has one variable in it, I can solve those fairly easily by now. I mean, we spent a long time covering that way back in chapter 2. So we are going to use the elimination method when the directions tell us to, but mostly when the equations are in standard form. Standard form, you may remember, you had slope-intercept form, you had point-slope form. Standard form, you have the variables on the same side. Kind of like ax plus by equals c, where a, b, and c are real numbers. A and b are not both 0. And typically we like a, b, and c to be integers, and we like a to be a positive integer, but we want standard form. We want the variables on the same side. Now, if we do it that way, you'll see how we can use that property of algebra and how we can eliminate one of the variables. Now, I have a pretty simple example. I mean, this is about as simple as it gets. Both of these equations are in standard form. It says use the elimination method to solve the system. So we're looking for the ordered pair that makes both true, satisfies both. So I want you to notice a couple things here. First off, they're both in standard form. See how the x's are lined up, the y's are lined up, the equal signs are lined up, the constant terms are lined up. That's what you want. You want that when you're doing the elimination method. And I also want you to point out something here. Look at the y's. The coefficient for the y in the top equation, because of the subtraction sign, is a -1. And in the bottom equation, it's a +1. And I want those to be opposites. I want to have one of the sets, either for the x's or for the y's, it doesn't matter which. In this case, for the y's, it's already set up, where the coefficients are opposites of one another. Because we know that when you add opposites, you get 0. So that's what we're going to use to eliminate one of the variables. We're going to eliminate the y's. Now, notice back here, see, it's the same system here. and that the y's are all set up. So if I use that property of algebra that says if A equals B and B or C equals D, then A plus C equals B plus D, I can add equal amounts to equal sides there. So I'm going to add the left side together, I'm going to add the right sides together. Now, because these are opposites, when I combine like terms, look what happens. 3x and 2x is 5x, but negative 1y plus 1y is 0y. This is just going to kind of disappear. On the other side, I get a 10. So the variable y has been eliminated, and I end up with an equation that just has the variable x, which I can solve. I divide both sides by 5, I get x is equal to 2. So I'm going to have a single answer because it says that the x is equal to 2, which means my answer is going to be something like 2 comma and then the y value. And just like we did with substitution, once I know the x, I will substitute it back into one of the two equations here, and I will solve for y. Now, when we were doing the substitution method, one of the equations was already like x in terms of y or y in terms of x, so it was very simple to plug in. In this case, that's not happening here because they're both in the original equations are in standard form. So my suggestion would be make it easy for yourself. Avoid fractions and decimals, avoid negatives when you can to make the arithmetic easier. So there's really nothing bad about either equation except that this one does have a minus sign, heaven forbid. I will probably take the bottom equation here and I will plug my 2 in for the x in the bottom equation. So that's what I've got down here. See if you can see this here. There's the bottom equation, 2x plus y equals 3. I had x was 2, so I plugged the 2 in right there. 2 times 2, 4. I solve for y, I subtract 4, I get y is negative 1. So the negative 1 is what goes right in here for the second part of my answer. So right over here, I have the ordered pair 2, negative 1, which you can write as a solution set. Remember, in some of the problems they were asking for the solution set. So we put the ordered pair in braces like that to represent the set of solutions. And we have one solution here. This system is consistent and it is independent. We have one answer. We classified the systems back earlier in this chapter. Now we can check our answer. I don't have the check written down here, but we could check our answer by taking this ordered pair and plugging it back into both equations. Now, the first equation, 3x minus y is equal to 7. If I plug 2 in for x and negative 1 in for y, I would get 6 plus 1 equals 7. I would get 7 equals 7. That checks out okay. If I was to plug it into the second equation, which was 2x plus y equals 3, plug the 2 in for the x and the negative 1 in for the y, I get 2 times 2 plus a negative 1 is equal to 3. I get 4 plus negative 1 is equal to 3. I get 3 is equal to 3. It makes both equations give true statements. It satisfies both. That's my solution. So that part of the thing hasn't changed as far as whether we were graphing or using substitution. With the elimination method, once you get your answer, you should check it to make sure. If it doesn't satisfy both, something's wrong. Either your check is wrong or your solving is wrong, or maybe both parts are wrong. So look through it again. So when we use the elimination method, remember, it must be in standard form, and we want one set of coefficients, it doesn't matter if it's the x's or the y's, to have opposite coefficients. Now, sometimes it's all set up for us, and sometimes it's not all set up for us. So you can see, and I've got a couple of examples here. In this next example, this one is all set up for part A. This one is all set up. Okay, excuse me while I'm talking and chewing on a mini donut at the same time there. Sorry about that. So what I'm going to do now, chew quickly here. I see how my x's are lined up, my y's are lined up, my equal signs are lined up, my constants are lined up. And on top of that, these have opposite signs, just kind of like the first example. This is like a negative 1y, this is like a positive 1y. Now we don't always eliminate the y's. But in this case, the problem was all set up for us to do so. So we might as well take advantage of that. So now I'm going to add the sides together. I'm going to add the left sides. I'm going to add the right sides. The right sides are easy. 4 and 8 is 12. Here, these are going to cancel out. That's going to give me 0y. Well, I'm not going to write 0y down again. I'm just going to recognize that this is 0 and this is 1x and 3x. So I have 4x. Well, I can solve this equation. I'm down to one variable. So I isolate it and I get x is equal to 3, which tells me that my answer is the ordered pair 3 something. Now I can plug back into either one of these two equations. And trust me, you can. I'm just not going to plug it into the top one because of the subtraction sign. I'm trying to avoid negatives to make it, easier for me. So I'm going to plug the 3 back into the bottom equation here. 3x, let's see if make sure this is on the screen so you can see this. 3x plus y is equal to 8. I'm going to plug the 3 in there for the x. So I get 3 times 3 plus y equals 8. I have 9 plus y equals 8. I'm going to subtract 9 from both sides. And I have y is equal to -1. So the -1, it's going to go right here. And this is my solution. Again, if they want a solution set, don't forget, just put the ordered pair in braces. Now again, I only had a single answer here, so this system is consistent and independent. That's okay, a lot of them are. Well, I'll show you what happens when we get one of the special cases here soon enough. Now let's try the second equation here, or the second system of equations here. I have x minus y is equal, x minus 2 is equal to the opposite of y, and I have 2x is equal to y plus 10. Now, unlike the first example, neither one of these equations is written in standard form. So I'm going to have to rewrite them first. So I left myself some room down here. Hopefully I left myself enough room. And I'm going to rewrite these. So I have x minus 2 is equal to the opposite of y. I'll start with that one. So x minus 2 is equal to the opposite of y. I am going to want to get this variable on this side and this constant on this side. So I am going to add y to both sides and add 2 to both sides. So I'm going to add y. Here, let me just write it out the long way. I'm going to add y and I'm going to add 2 to both sides. I'm going to add y and I'm going to add 2. That way these 2's will cancel and these y's will cancel. And I'll have x plus y is equal to positive 2. First guy is ready to go. Now the second equation, I have 2x is equal to y plus 10. I think all I have to do here is subtract y from both sides. And if I subtract y, I get 2x minus y is equal to a positive 10. Now for the third time, and it doesn't happen this time every time, but for the third example in a row, when I look at these two equations in standard form, in fact, I'll just put this equation right over here underneath it. Do you see how in standard form the x's are lined up, the y's are lined up, the equal signs, the constants, and I have my y's already with opposite coefficients. This is like a -1, this is like a +1. I'm ready to go. So I add up the left sides, I add up the right sides. On the left sides, combine like terms, the y's cancel, I get 3x, because that's like a 1x. Here I get 12, and now it's easy pleasy. Divide by 3, I get x is equal to 4. All right, so that tells me that my answer is going to be the ordered pair 4 comma something. It's the x value, so it goes in the first part of the ordered pair. Go back and plug this in and solve either one. Doesn't matter which equation. I'm going to take the bottom equation and I'm going to solve for y by plugging the 4 in right there for x. So that's 2 times 4 is equal to y plus 10. So I have 8 equals y plus 10. I'm going to subtract 10 from both sides. And I get y is equal to -2. That goes right in there. So there's my solution, and here's my solution set. All right. Now, again, check your answers if you're unsure, because there's lots of lots of places for mistakes. I do a lot of steps here. The more steps you have, the more possibility or opportunity for a silly mistake to be made. So you can plug the 4 in for the x and the -2 in for the y. The 4 in for the x, and then negative 2 in for y. And you can either do it in your head or do it on paper and check your answers. Now, up to this point, we've had some good examples, but we've had all of our examples mostly be set up for us. So what we're going to do is we're going to show an example where it's not all set up for us, that the coefficients are not all lined up perfectly for us. So in this example, I have the system 2x minus 3y is equal to 6, 3x plus y is equal to negative 2. They're both in standard form, that's good. But look at your coefficients. Here it's a 2 and a 3. Those are not opposites. Here it's a negative 3 and a positive 1. Those are not opposites. So I can't just add them up as is. I have to use the fact that the multiplication property of equality allows me to multiply both sides of an equation by the same non-zero number. I'll say that again. I'm going to have to use the fact that the multiplication property of equality allows me to multiply both sides of an equation by the same number, the same non-zero number. I can multiply the left side by 5, the right side by 5. The left side by negative 2, the right side by negative 2, as long as it's the same number. So I'm looking at this, and here it is again, just written again for me. I'm looking at this and I'm thinking, hey, even though these are not the same coefficients, this is a negative 3, this is a positive 1, they at least have different signs. One's negative, one's positive. That's not the case for the x's. Here the x's are both having positive coefficients. And I'm looking at this, and I'm looking at this number 3 here. I know it's a negative 3, but I'm looking at the 3, I'm looking at the 1 here, and I'm thinking 3 is a multiple of 1. If I was to take the bottom equation and multiply by 3, leave the top equation the same. There it is. It's the same. I didn't change it. 2x minus 3y equals 6. 2x minus 3y equals 6. That stays the same this time. But I'm going to multiply the bottom equation by 3. That's my little notation, that I'm multiplying this bottom equation through by 3. 3 times this term, times this term, times this term. Every term on both sides. You have to multiply every term on both sides by the same number. And so that becomes a 9x, that becomes a plus 3y, and that becomes a minus or negative 6. Now, this is equivalent to this equation here. It's just a multiple, constant multiple of it. But look at my variables now. Look at my y's. They are all set to cancel out if I was to go ahead and combine sides, add both sides together. X's are lined up, y's are lined up, equal signs are lined up, constants are lined up. So if I add the sides, this minus 3y and this plus 3y, that's just 0. They cancel out. I have, it looks like 11x equals, and then on the right side, a positive 6 and negative 6 is 0. Now don't panic if you get a 0. Sometimes 0 pops in. But I'm going to solve for x. I'm going to divide both sides by 11, and I get x is 0, which tells me that my answer is 0 something. Now, you can already see the something because this is an example that was already worked out. But the x value is 0. I can take that as 0. I can go back to either one of my equations here. And I took the bottom one because I tried to avoid this minus sign. And I plug a 0 in for x. This 0 goes right in for x. And I have 3 times 0 plus y is negative 2. I have y is negative 2. That's the second part of my ordered pair. So my solution set, if they ask for the solution set, again, it's one ordered pair. It's the ordered pair 0, negative 2. Plug back into both equations, the 0 and the negative 2, and for the x and y respectively. See if you don't satisfy both equations. Now, in this example, I had to multiply one of the equations through by a number. Sometimes that occurs. Sometimes you have to multiply one equation through by a number and the other equation through by a different number so that it's set up. And that's what happens here with example A. Solve the system using elimination. Now, both of these equations are in standard form. See how the x's are lined up, the y's are lined up, the equal signs, the constants? It's perfect. But neither one of these set of coefficients here are opposites. Now, at least the y's have opposite signs, but they're not the same number. So there is no nice, neat number that I can multiply times 5 and make it an 8. I mean, I can use a fraction, but I don't want to do the fraction if I can avoid it and make a silly arithmetic here. And there is no nice neat number that I can multiply times 8 to make it a negative, or to make it a 5. So what I'm going to have to do here is I'm going to have to use the least common multiple effect. I look for the smallest number that is a multiple of 5 and 8, and it's 40. 40 is my least common multiple. And again, I'm using the y's not because it's always the y's, but because at least they have the opposite signs working here. The x's are both positive. So if I was working on the x's, I could do this. I just have to make one of the coefficients negative. And my least common multiple would be 6, a little smaller than 40, but still not terrible. So I'm going to take this top equation right here, and to make that a negative 40, I'm going to have to multiply by a positive 8. Every term, both sides. So that's 24x minus 40y is equal to 200. Number got a little bit bigger. Then I'm going to take the bottom equation, I'm going to make that a positive 40. I'm going to multiply it by 5. I'm going to multiply by 5. 5 times every term in both sides of the second equation. So that's going to give me 10x plus 40y is equal to, looks like negative 30. And then I'm going to combine. Well, these cancel. I get 34x is equal to, it looks like 170. Well, I'm running out of space here a little bit, but I'm going to divide both sides by 34 and try to get the x. And if I'm lucky, 34 will divide into 170 evenly, and it does. It goes in 5 times. So x is 5. So that tells me that my answer, and I'm running out of space here, so I'll bring it over to here. My answer is going to be 5 comma something. Now remember, my original equations back here, I'm going to plug 5 back into either one of these for x and solve for y. I'm taking the bottom one. Again, no subtractions. So let me write that bottom equation down here. Since it's on the other sheet, I'm going to plug 5 in for x. 2 times 5 plus 8y is equal to negative 6. This is 10 plus 8y is equal to negative 6. I subtract 10 from both sides as I isolate the variable, or attempt to. And I get 8y is equal to, looks like negative 16. And then I divide by 8, both sides. And I get, when it comes out to be an integer, I get a negative 2. So that tells me there's a negative 2 that goes right there. There's my solution. I can write my solution set with braces. All right, now the next equation, there's a system of equations. 4x minus 5y. I keep seeing that I have all these examples where it looks like the y's are your best bet to cancel out. Tell you, I'm going to bust the trend here. I'm going to eliminate the x's this time. Now I know that the y's would be easier. Now neither one of these are multiples of each other, neither one of these are multiples of each other, but at least the signs are different. And they're in standard form. The x's over the x's, the y's over the y's, equal signs over the equal signs, constants over the constants. But just to show you that it works, and you don't always have to eliminate the y, as I've done in probably the last 4 or 5 examples I worked out, I'm going to eliminate the x. Now to do that, one of these has to be positive and one of these has to be negative. And my least common multiple for 4 and 3 is 12. So I either need this to be a negative 12 or this to be a negative 12. I'm going to just do the top one. I'm going to make the top one a negative 12. And to do that, what times 4 is negative 12? Well, it'd be negative 3. So I'm going to multiply negative 3. Now, be careful here with the negatives because of the signs. Negative 3 times 4x is negative 12x. Negative 3 times minus 5y is plus 5y. And negative 3 times a negative 18 is a positive 54. Wait a minute, 15. It'd be nice if I wrote it down right. I think I said 15. If I didn't, I apologize. I'm multiplying by negative 3. So that becomes a positive 15y. All right, now the next one, I just want it to be a positive 12 here. So I'm going to multiply by 4 every term both sides. 12x plus 8y is equal to negative 8. And now everything's looking good. My x's are set to cancel because they have opposite coefficients. These add up to 0, and I have 23y equals, now a negative 54, excuse me, a positive 54 and a negative 8 is a positive 46. I divide both sides by 23, and I have y is equal to 2. So I have y is equal to 2. I thought I had something, no, I guess not. Anyway, so my ordered pair is something, comma, 2. So this time I solve for the y first, so that goes into the second spot because that's the y coordinate. I go back and I plug into either equation. Just for the heck of it, I'll plug it into the bottom one here. 3x plus 2 times y, which is 2, equals negative 2. 3x plus 4 is equal to negative 2. I'm going to subtract 4 from both sides. See all the steps? Really got to be alert, focused, and careful not to make a mistake because there are so many steps. One mistake, especially early on, is going to mess up the whole problem for you. And I get x is negative 2, which goes right there. And there's my answer. And again, you can plug negative 2 in for the x and a positive 2 in for the y and see if you don't get a true statement. All right. Now this example is very much like the other ones. I'm going to get to the special cases here in just a second. This one's also going to be independent and consistent here. I'm going to have a single answer. It's just that it's not already written for me in standard form. So what I'm going to do here, is, or at least the bottom equation is not in standard form. The top one's okay. 4x plus 9y equals 3. That one's good to go. But this one here, I'm going to have to add 3x to both sides. So I can get the variable on both on the same side here. These cancel, and I get, I'm going to switch the order, right? This is 3x plus 5y is equal to 6. So I'll put him under here. 3x plus 5y is equal to 6. Now, in this problem, whereas in the last problem I had more of a choice, I just went ahead and kind of bucked the trend. In this one, it's really not set up for either variable to cancel out. I mean, I have them, x's lined up, y's lined up, equal signs lined up, constants lined up. But here, the coefficients are both positive for the x's, they're both positive for the y's. So no matter which variable I try to cancel out, I'm going to have to multiply through by a negative, as I showed you in the last example. Now, the only thing that the least common multiple here for the coefficients of the x's are 12. Here it's 45, a little bit bigger number. I might just go after this guy and try to make one of these a positive 12 and one of these a negative 12. To make the top one, let's say I'll make it the negative. I have to multiply by negative 3. So this becomes negative 12x minus 27y equals negative 9. I multiply each term by negative 3. Signs change. This one, I'm going to make it a positive 12 by multiplying by 4. So that would be 12x plus 20y is equal to 24. The 4 times each one of the terms. When I go ahead and combine these, the x's are canceling out, as I hoped. This gives me negative 7y, careful with your signs, and then over here, looks like I'm going to get a positive 15. I hope I wrote this problem down right. I don't remember any of them with fractions. Maybe that's why I used the whole page when I did this the first time. So I'm going to divide both sides by negative 7. I had pretty good luck avoiding fractions until now. And I have y equals 15 over negative 7, or negative 15 sevenths. So that means my answer is something negative 15 sevenths. Unless I made a silly mistake. Let me double check here that I didn't write down something incorrectly. Let's see, times negative 3. I seem like I make a mistake just about every video anymore, so I don't want to keep doing that. Kind of looks like I've got it set up right here. So if my answer here has a y value that's negative 15, hang on a second here real quick. That's a negative 15 sevenths. Then what I have to do here is I have to take the negative 15 sevenths and go back to either one of these two equations. Now, you can have fractions no matter which one you take. I'm just going to take the top one because of all the positive here. and plug the negative 15/7 in for y. So it's a little bit of arithmetic, because I have to multiply the 9 times the negative 15/7. I'm going to write the 9 as 9 over 1. Positive times negative is negative, so I know it's going to be a negative. And let's see, nothing cross cancels, so it looks like I'm going to get minus 135/7 equals 3. Yikes! I'm going to have to add 135/7 to both sides to get the x by itself, so I'm going to have to get a common denominator over here on the right. And I get 4x is equal to, now my common denominator would be 7. So this would be 21/7 plus 135/7. So I get 4x is equal to 156/7. Now 7 doesn't divide into it evenly, so I'm going to leave it like this. But now I got to get rid of the 4 that's times the variable by dividing both sides by 4. So if I divide the left side by 4, and I'm going to divide the right side by 4, now when you divide a fraction by a number, you have to multiply by the reciprocal of the number. So I'm just going to go ahead and change this to times 1/4, because that's the same as dividing by 4. Now I think 4 goes into both of these. I can cross cancel a little bit. 4 goes into that once, 4 goes into that. It looks like 39 times, so I end up with 39/7, if I didn't make a mistake, which really doesn't simplify unless you want to change it to a mixed number. So way up here, 39/7 from this value. Now this one would be a peach if you had to take this answer, go back to both of these equations, plug them in for x and y, and show that you have a true statement. Lots of arithmetic there with fractions. It can happen. Last but not least, two special cases. Okay, my two special cases, oh by the way, notice here, I went ahead and showed you in this example the same last problem, but instead of canceling out the x's, I canceled out the y's. See how it still gives you the same x value? I have 39/7 here, I have 39/7 here. Just to show you, either way, sometimes one method works better than the other. Okay, just, you know, kind of be careful with that and approach it carefully there. Make sure of your arithmetic. All right, now the last two examples are my two special cases, because every problem I've done up to this point has had a single ordered pair answer, and we know that with a system sometimes there's no solution, that the lines might be parallel, and sometimes there's infinitely many solutions because the lines might be the same line, they might coincide. So I'm going to show you what happens. That's easy to spot when you're graphing, and it's not that tough to spot when you're using substitution. And if you can spot it for substitution, you can spot it for the elimination method. Now look at the two examples here. Start off with example A. 8x, I think that's an 8. No, that's a 3. Gosh, I can't even read. 3x plus y is equal to -7. 6x plus 2y is equal to 5. I'm going to try to get the y's to be eliminated here. So I'm going to take this top equation and I'm going to multiply by -2. That gives me -6x minus 2y equals 14. I'm going to leave this equation exactly the same. And you see how my y's are going to cancel? Just like I had hoped. Then I combine my x's and they cancel. So I get 0 on the left side, and on the right side I get 19. So you know something special is going on when one variable that you choose to eliminate also leads to the other variable being eliminated. So they both drop out, and you're left in this case with a false statement. Now, think about it common sense. My two possible special cases are no answers or infinitely many answers, and I have a false statement. Does that sound like a false statement might imply 0 answers or infinitely many answers? I'm hoping you said 0 answers, because this is a false statement, means it's a contradiction. It's not going to work no matter what you plug in for x and y. So therefore, empty set. Now don't get me wrong, this has infinitely many answers and this has infinitely many answers. They just don't have any answers in common. If you were to graph these two lines, they'd be parallel to one another. They'd both have slope -3, but they'd have different y-intercepts. Okay, over here, I have 2, that's an x there, that's kind of hard to read. I have 2x plus 5y equals 1, negative 4x minus 10y equals negative 2. I'm going to take the top equation, I'm just going to bring it straight down here, and I'm going to multiply by 2. That'll give me 4x plus 10y equals 2. I'm trying to get the x's to cancel out, and by multiplying it by 2, I get opposites here. This one I'm just going to leave the same. So that's negative 4x minus 10y equals negative 2. So when I go to combine, the x's do cancel, but so do the y's. 0 on the left side, and on the right side, I get 0. I get a true statement. This one was a false statement. This one's a true statement. So that's how you can tell which one of the two special cases you end up with. In this case, it is the set of all ordered pairs on either line. So we write that as the set of all ordered pairs x, y, such that, and then we can write either equation down. 2x plus 5y equals 1 works. I got to use the other one as well. And that's what happens with the special cases. So be looking for them because they'll throw those in from time to time. Anyway, that's your solution there for part B. This is going to take a little bit of practice and a little bit of perseverance and some paper and a sharp pencil. So make sure that you take the time and you practice, practice, practice.